Okay, hello. In this video, we are going to do examples from data structures that we covered towards the end of CS202, the ones that will be on the final exam. So we'll be looking at btree, heap, skip list, AVL tree, and try. Or at least we'll see how far we get in one video. We'll start with the heap. We'll draw a picture over here, and we're to go through. Let's say that we're going to do a min heap. And we're going to go through and insert these numbers, some number of them, until we don't feel like inserting any more of them. Okay, and so you want to recall the basic idea of a heap is, pause the video and tell yourself. All right, the basic idea is a binary tree where the property is that each node is smaller than the ones below it. Okay, that's it. So we always have the smallest node. When we're looking at a min heap, we always have the smallest thing on top. Let's just go ahead and start inserting things here. To start off with, we have a 10. All right, and we'll put that up here as already inserted. And then we want to go and put a 28. There's isn't particularly getting too interesting yet, so we'll just put the 28 right here below the 10. All right, and the question is, where would the so this is how we think of it, and we'll go ahead and do this right. We'll put in what the array would look like as well. That will look like over here. Put this on the bottom. So we'll have index and value. And we'll do this in 6-foot font so it lines up. All right. Just a second. Okay, so at this point we have at index 0 the value 10, and at index 1 the value 28. All right, now we come in and insert the value 27. The natural place to put that in the array here, if we're viewing things in terms of an array, at index 2, we would put the value 27. In terms of our picture here, and we'll say something about how the picture corresponds to the array. So this is 28. 27 there, and we're only going to make adjustments if we break this property here. So far we haven't had to. The next node will be a 19, and we fill this picture in from left to right. So we would put a 19 here. And now we need to make some adjustments. So every time we put something new in here, we check to see, is this larger than its parent? So the 19 is smaller than its parent, that means we're out of order here. The ones towards the top are supposed to be smaller. And when we put this in here, we would have a 19 there in index 3. All right. If we're looking at the array version, that's out of order. We want to swap the 19 and the 28. And that would be like over here in our array picture. We have it like this. All right, and now the heap property is satisfied again. All the nodes are smaller than the children. And we keep going. We put 25 in and we go from left to right here. So we put a 25. And that's okay. 25 is larger than 19. So we go for the next one. 18. As one of the children of 27 here. And now we have a problem. So what are we supposed to do to fix it? We swap these two. All right. And let's take one more. Let's take the 13. So if we put the 13 in, we'll have another child of the 18 here. We put the 13 there. And now that is out of order with the 18. So we'd have the 13 here and 18 here. That would be what the picture looks like. Okay, so let's say something about the array. The way this heap picture is stored is actually in an array. Okay, and I'm going to put, right now we have 1, 2, 3, 4, 5, 6, 7 numbers. And that should fit something like this. And let me take these values out. There's 7 indexes. And the way the picture goes, let's see. All right, index 0 is the root. We think of it as the root. And its children are there at 0 and 1. Index 1 and 2. So if that's what if my picture is supposed to go like this, then at index 1 I would have 19, index 2 I would have 13. Okay, and then we would just keep going. This let's draw this a little bit better. Hold on. All right, let's go with the picture like this. So we have this 0 here. Its children are 19 and 13. So there's the 19 and 13. Now the 19 has 2 children as well. And we're going to say that in the array, they're just in the next spot. So the child of 19 there, which should be 28, will just be in the next spot in the array. There's another child of 19, which we'll put in the next spot in the array. All right, so we're filling in the children that we need. Each node needs to have 2 children, and we just fill them in from left to right. Now we have node in index 2 here. This 13 needs to have 2 children, 27 and 28. We'll just fill those in the next spots in the array, 27 and 18 there. So if we're drawing the picture, we've got node 2 here. And this one. Okay. All right, so that would be our picture. The cute thing about drawing the picture like this is if I'm at any node here, if I'm at index 2, then the way I get to my children is I multiply by 2 and add 1. So I multiply by the index. I'm at index 2, multiply by 2 and add 1. Multiply by 2 and add 2. If I'm in index 1 here, to get to my children, multiply by 2 and add 1. Multiply by 2 and add 2. Okay, so for the test, I'm just going to ask you to draw the picture like this. You put things in like this. When you have to put something new in, you go from left to right. As long as you get the picture right, that's okay. The way this is actually stored and the way the code would actually work is with this in the array. So note node at index I, its children are at index 2i plus 1 and 2i plus 2. Note node at index I, its parent is at what index? So if we look at 4 here, its parent is 1. We also have 3 has 1 as a parent. If we go to 5, its parent is at 2. 6's parent is at 2. So the formula would be something like I minus 1 over 2. So you roughly multiply by 2 in the array to get to your children. You roughly divide by 2 to get to your parent. And that's pretty cool. We don't have to store pointers. You just get between parents and children with indexing in the array. All right, let's see what will happen next. I'm not going to update the array anymore. I'm going to leave the array here based on this picture. Just going to work on the picture now. It'll be a little bit faster to get through some more. Okay, so we want to put 23 in. The rule is you put it in the next spot. Okay, so the next spot that's open, if we sort of go top down, left to right, is there. All right, and that would be 23. The rule is you're supposed to be smaller than your parent. You're supposed to be larger than your parent. These are out of order. So I've switched them. This is 28. This is 23. All right, let's go another one. If we're going to put 7 in, where do we put it in? I'm going to add a new node. Where should I link it up? So this is going to be 7 here. All right, I just link it up right here. We put it in the next available spot, going left to right across the bottom layer, and then we fix. So we fix it. We just go and look at its parent. Is 7 smaller than 23? Yes, we need to switch. So that would be 23, and now this would be 7. Now we want to look 7 versus its new parent. New parent is 19, that's out of order, so we need to switch those. And then again we need to check, they're out of order, so we're going to switch those. And now that's all okay. Let's put one more in. So we're going to add 6 and go ahead and pause and tell yourself where's it going to go and how are things going to change. Okay, hopefully you paused and said what you think is going to happen. Now we'll go ahead and put it in. So there's the 6, and it would get connected to the next available spot. All right, and then we just go up the line to check to make sure when we need to do switches. Those are out of order. We put 6 there. Check it again. It's out of order, so we can switch the 10 and the 6. Out of order. Switch them again. All right, and that's it. And we'll stop there. And now if we wanted to update the array, index 0, question for you is, what would be an index 0 now in the array representation? That would be 6. So the ordering on the array, this is index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if I asked you what's at a given index in the array, it actually is the order that you would count them off. All right, I think that's about all we want to do for a heap. The question on the exam will be do some inserts and draw the picture. Let's see, we'll do one more little thing. Okay, we have to do something else with the heap here before we're done. The whole point of a heap is that you can have the smallest, and sometimes you want to take the smallest off. All right, so we've inserted. Now we want to remove. So our next operation that we'll do is remove the top, or whatever we want to call that. Okay, maybe we're going to call that top, or something else. All right, so I'm going to take this 6 off. I have an empty node there, and I need to put something there. And one thing that you might think to do is take the 7 and put it there. That's going to be the smallest. That's what will end up happening. What ends up being the more elegant way to do it is I have an empty node here, and generally if I have a heap with one less number of nodes, it really should be that this isn't there. Right? If we're filling in from left to right and we removed one, we would normally remove the last one we added. So what I'm going to do is take the 25, the last node, put it on the top. Okay, now I have to check and see if there's a problem. So 25 is larger than both of its children. It's a problem. Should I switch it with the 13 or with the 7? If I switched it with the 13, then that would be moving the 25 down, which is good, but now the 13 has a problem with the 7. So that's the wrong decision. I'm going to look at putting this 25 down, and I'm going to move it to the smaller of its children. So there's the 25, and the smaller of its children goes up. And now the 7 is okay, it's smaller than 13, and I have to look at the 25. Is it larger than either of its children? It's larger than both. And the right thing to do is to move it to the smaller of its children. Okay, so when we insert new node for that n, check with parent, swap if needed, repeatedly check parent. All right, that's what we did when we added new node. You check to see if it needs to swap with his parent. Does it need to swap with his parent? Does it need to swap? All right, that was on inserting. Remove top. So what do? We take it off. The last node at top. That's what's putting the 25 at the top. Check if larger than the children. If yes, then swap with smallest child. Repeat. Okay, so that's what we did. The 25 was here. We had a 7 and a 13. We swapped it with the 7. And we keep doing that, moving it down the tree. All right, things you're supposed to know. So note, operations are big O, depth of the tree, which is going to be big O of log n, if n is the number of things in the tree. When we do an insert, we put it at the end. We possibly have to move it up. When we do a remove from the top, we put something at the top, and it sort of goes down. All right, that's a heap, and that was all done with that one. All right, we'll do a btree next. And we'll do the same sequence of inserts. All right. So the point of a heap is you have the smallest at the top. If you're in a situation where you're keeping track of some information and all you need is the smallest, a heap is a good thing. It keeps track of the smallest. All right, a btree. We'll use the same sequence of inserts and maybe some more. So we're going to do this. The thing to remember about a btree is it's like a binary search tree, but with more than 2 children per node. We're going to do each node as 2 to 4, 3 to 5 children, and has 2 to 4 items inside the node. All right, so I'm going to show this at the beginning. We're going to start off like this, and let's see. We're going to do it like this. Okay, so a btree node actually has more than just one item inside of it. This one here, this is actually an array. So a single node is actually an array, where we could think of it as we have index 0, 1, 2, and 3, and at those entries are 10, 28, 27, and 19. To make the picture smaller, I'm just going to put the values there. So the node has those values inside of it, and we would already have those items that we wanted to insert. But they should be in order. So it will keep them in order. All right, so that's how it would be storing them in an array or something else inside of that node. So a single node is like this. This is the root. Now when we go to insert 25, it should go right here, but there's not room. I only have room for 4 there. That's what I'm saying the rule is. So it's going to need to split. Just a second. Okay, so, right, this is where we would have been. That's too much. So what we do is we're going to split this into 3 different nodes. the smaller ones on the left, the larger ones on the right, and the middle one in the middle. Alright, so this is what we would have, and the order here at the present time would be something like this. We have 25 at the root. Things that are less than 25 are over here. Things that are greater than 25 are over here. So let's see what would happen when we put 18. So if we want to put 18 in, we have a 25. We know things that are less than 25 are over here. So 18 should go over to this node. Alright, so that's 18. 13, the same thing will happen. It's less than 25, it should go over here. Now, 23. 23 is less than 25. It should go over here. But now that's too many. We're not allowed to have 5, we're only allowed to have 4. So this needs to split. We're going to split it into 3 copies. The smaller ones would be there. The larger ones would be here, and we have the middle one. Okay, now that could be like this, but actually this 18 key doesn't need to go on this level, it can go up here. So the picture should look like this. Now the root has 2 keys again, and anything that's smaller than 18 is over here. Anything that's between 18 and 25 is here, and anything that's larger than 25 is over here. Alright, and the 23 is now in there. What happens when we put a 7? That would go over here, and if we put the 6 in, that would also go over here. Put a few more in. So the next ones that we would have done, we'll copy and paste this whole sequence in here and use some of them. Okay, so if we put a 30 in, that's larger than 25, that goes on this one, 30. Where would the 17 go? 17 would go here, less than 18, and that would need to split again. So I'll have to shift everybody over again. So this is going to split into 2 parts. There's still room to push somebody up to the top. So we'll push that 17. Let's see, we have the lower 2 there, we're going to have the larger 2 here, and then the middle one is going to get pushed up to the top. So now we have things that are smaller than 10, things that are between 10 and 18, things that are between 18 and 25, and things that are larger than 25. That's the picture that we have now, and 17 is in there. 15 is between 10 and 18, so that goes into this one. 8 is less than 10, so it goes over here. 20 is between 18 and 25, so it goes here. 3 and 1 are both less than 10, so they're going to go over into this one. And we need to split again because there's 5. So this is going to split, and the 6 is going to move up. So there will be a 6 there. And we'll have two nodes here instead of 1. We'll have the lower items on one and the larger items on another. Like this so that it fits in the picture. So now we have the things that are less than 6 and the things that are between 6 and 10. If we keep going a little bit more, there's 5 would go here less than 6. Here are those spaces so it fits. 11 is between 10 and 18, so that would go in this one. And 22 is between 18 and 25, that goes here. 14 would go here. And we have a problem, we need to split again. So 14 would need to go into this one. So 14 would need to go up here. We'll have to deal with that because that's a problem. There's 5 numbers there. Let's get this sorted out first. Okay, so we split that node. The one that's just above it, so that gets pushed up. I'm going to get rid of all of these for a second. Alright, so now we're in the situation where this node here also is too big, so it would get split. And with one more higher. So we have the things, 2 smaller ones right there, the 2 larger ones right there, and the one in the middle. Alright, and then we would have the corresponding arrows going between all of these. Things that are less than 14. Things that are greater than 14. And over here, things that are less than 6. Things between 6 and 10. Things that are greater than 10. And from this Let's see, how do we get here? This one. Right, so this one here was between these, so it's going to be, when this node splits, it has all of these that were children, and this one is going to come from things that are less than 18 and bigger than 14. And in between 18 and 25, and greater than 25. All right, so that is the way the btree inserts go. And let's say, all right, let's reflect on what we're doing here. So we have each node has 3 to 5 children and has 2 to 4 items inside the node except the root, and we have fewer. So right here our root node only has 1 item inside of it and 2 children. Normally the number of children would be hundreds or thousands. The reason is the more children you have, the smaller the depth. This makes for very small depth, like 4. So we can potentially make it so the depth is never more than 4, which would be awesome. The point is to keep the depth small. If we can fit each node, so each node is potentially having hundreds of things inside of it, inside of one read from disk, and we have a small number of disk operations. So what we're thinking of here is terabytes of data, billions, trillions of nodes potentially, and we're not going to fit this whole data structure in memory. We have to store it onto a physical long-term storage disk or drive or something where the cost of operations is pretty high to read a chunk. So each chunk is small, but the number of chunks that we have to read is what we want to minimize. All right, so in a tree, any operation is based on the depth of the tree. So we want to keep the depth small, then the number of chunks that we have to read will be small. Okay, so this was our insert. So for an insert, the new item where it should be on the leaves, and possibly split and over full leaf, and middle item. That's what we did here. If we inserted something new here, let's say the next one, let's say that we got a 24. So if we put a 24 here, then we would split that, and the middle item of it, 22, would go up. That was our algorithm. All right, on a delete, let's say that we need to delete something. Okay, let's just say we're going to delete 22. So we go and we find the 22 and we get rid of it. All right, that would be fine. Now, what if we need to delete 8? All right, we go and delete 8. And there's something we have to fix. this node here now only has one item inside of it, and the rule that we want to keep is that there are always 2 to 4 items inside of each node. On inserting, we get to have problems when there get to be too many. On deleting, we get to have problems when there aren't enough. Alright, so the natural thing to do is to merge. So this doesn't have enough items. If there's a sibling here that has room, we just move it over. Okay, so it doesn't matter, we could move it over either way. Let's say that we moved it over this way, and this would go away. Okay, does that make sense now? Or do we need to fix something? Okay, so now we have a problem where there's a pointer here to something that doesn't exist anymore. And if we have 2 keys here, then there should really be 3 children. That's the way it works. We have 2 items here. There's less than, greater than, and in between. So if we're going to have the 7 over here, then that really means there's only one thing that we need up here. So the 6 or the 10, one of those should really come down. Let's say the 6. And the 6 is really over here. Now all the leaves look okay, but this node here is under full. And if we look at things again, we have the 10, 14, 18, and 25. Those are the items in the top 2 levels. There's only 4 of those now, and they would fit into one node. So I could put this back into one node since I've deleted enough things with 10, 14, 18, and 25. And update all those arrows. So the things that are less than 10, right, we have an issue here. So this is not a valid picture. This would only make sense if we had the 10 there and the 7 here. All right. So let's just say this is where we ended up. So we'd be back to only needing 2 levels here. All right, so on delete, we remove, and if the leaf becomes under full, then we need to either borrow from a sibling or merge sibling. Okay, so an easier thing would be, let's say that we get rid of 23. And let's get rid of 20. All right, now in this setting, 19 is by itself, so that's not okay. What would be nice is if we could just borrow this 27. Okay. So can we just put it over here? Now this 25 is an issue because, well, Those are things that are bigger than 25. These are supposed to be things between 18 and 25. That's not true, so what we should really do is the 25 should be here, and the 27 should be here. So the leftmost, the smallest one from here went up, and this one came down. And now that looks okay. Alright, so what you should do for the test is if we do inserts, you're going to be doing these splitting in the right way, and then if there's a delete, and I give you a hint on how you're supposed to split, draw the picture correctly. Let's see where we're at. So we have heap done, btree done. Why don't we leave the other two for another video?